Now that we know that Grassmannians are projective varieties, we can ask what are their properties. So can we find the dimension? Is it reducible, non-reducible, and so on? And to understand this better, well, note that this Grassmannian sits inside this big projective space, and this, of course, has a cover by affine spaces. And so if we intersect the Grassmannian with this cover, we get the cover UI of the Grassmannian. And it turns out this is not just an affine cover, as we know, but it's actually a very simple cover. We can find a simple description of these patches, and this allows us to explicitly prove some properties of the Grassmannian. And the construction is as follows. So let U0, as above, now be the open subset where, well, one of the coordinates, one of the Plücker coordinates doesn't vanish. And so we take, for simplicity, just the first one, the Plücker coordinate for this basis element of the alternating tensor product. And so consider U0 to be the subset where this doesn't vanish. Then, well, linear space is contained in there if and only if, well, the linear space is the column span of a certain matrix here. So it's an n cross k matrix. And the coefficient of this thing was the first maximal minor, so the maximal minor of the first k rows here. So if you partition the matrix into parts A and B, a k cross k matrix and n minus k cross k matrix B, then the condition of being in U0 just means this minor here is non-zero. In other words, A is an invertible matrix. And then what we can do, we know that we can modify this matrix by column operations, by multiplying from the right with some invertible matrix, because it doesn't change the column span. And, well, we have a very nice invertible matrix, namely A inverse. And if we multiply this from the right, we see this exactly converts the upper part into the identity matrix and the lower part just to the matrix B times A inverse. And so we have converted this into this format, and this shows that U0 is exactly the image of a certain map F from some affine space. This is an affine space which parameterizes n minus k cross k matrices to U0 inside the Grassmannian by sending this matrix to the column span of this discomposed matrix. And we check now that F has very nice properties. In fact, we will show that F is an isomorphism from this affine space to U0. So let's get on this. So the argument above shows if we are in U0, then we are the column span of such a matrix. So this shows F is surjective. Furthermore, what are the Plücker coordinates of F of C? Well, they're the maximal minors of this matrix here. And you see these determinants all depend in a polynomial way on the entries of this matrix C. And so we see that somehow, you see F lands in one of the patches of this, if we go up again, it lands in one of the patches of this projective space, namely the kind of zeroth patch. And this is an affine space, right? This is an A n choose k minus 1. And then F, the claim is that because all of the coordinates of this morphism, or all of the coordinates of this map are polynomials, we know a map to an is a morphism if and only if the entries are kind of regular functions. And so this shows that F is indeed a morphism as we wanted. And for the last part, we also want to show it's injective. So for this, we want to see that from this image, so from this column span, we can reconstruct the entries of C. But somehow, if you look at this, matrix, so first of all, if we are given such a linear space here, the column span of such a matrix, the first claim is that we can actually reconstruct the matrix itself, because in this linear span there will be unique vectors which start with these kind of patterns 1, 0, 0, 0, 0, and so on. So there's a unique basis which has this upper part. This you can convince yourself of. And so, in fact, only knowing this linear space in the Grassmannian actually allows us to reconstruct exactly this matrix here. And then, for example, you can, so this already kind of shows the injectivity. The way that you can now reconstruct the Cij is actually as a minor of this matrix here, because so for example, let's do it just in an example, because that's very straightforward. So somehow assume you have this matrix here, and you want to reconstruct, for example, C12 from the matrix using only minors. Then you can do this by taking the first and the third row of the matrix, and then the determinant is exactly C12. And similarly, if you want to reconstruct, for example, C11, then you would choose this row and this row, and then you get it as minus a determinant of this subthing. And so what this shows is that all of these entries here are minors of this big matrix. And we know the minors of these matrices, these are exactly the Plücker coordinates. The Plücker coordinates that we have on this big projector space. And this shows that not only is F injective and we can write down F inverse as a set map, but actually we can write down F inverse as a morphism. And so this completes the proof that F is an isomorphism. And so somehow this sends this affine space, this matrix space, as an open subset of this Grassmannian. And we did the argument now for the patch U1 or U0, but in fact the other patches, of course, work similarly, and they cover all of the Grassmannians. So somehow this Grassmannian has a cover by these affine spaces. And that's good enough to show some nice topological properties, namely that the Grassmannian is an irreducible projective variety of dimension n minus k times k. And well, this thing is covered by these sets, and these are irreducible and of the dimension that we claim. And also, any two of them have non-trivial intersection. So to show this, there's kind of two ways. You can try to write down a concrete n cross k matrix such that all k cross k minors are non-zero. Once you have this, this would be the column span of this would lie in all of these affine patches. So you can either give a concrete example, or if you want to have a kind of slick way, if you're lazy, like me, then you can also observe that the space of n cross k matrices, of all matrices, is an irreducible space. It's just a big affine space. And the condition for any single of the minors that the minor is non-zero is a Zariski open condition in this irreducible space. But we know that the intersection of two non-empty, the intersection of two non-empty open subsets of an irreducible space is non-empty. And so in particular, also these finite intersections are still non-empty. And so without writing down basically any example, you can show that such a thing must exist. That's a kind of nice way that allows you to avoid having to write down an example. So in whatever way, shape, or form you prove this, you can show that you have this cover with non-trivial intersections. And then it was on an exercise sheet and also in the script in these exercises here, that if you have a space, it's covered by irreducible open subsets intersecting non-trivially, it's irreducible. And if it's covered by open subsets, all of the same dimension, like this, and any of them intersect, then it also has this dimension as desired. And so this finishes the proof. Once we know these affine patches, we can conclude about the entire space. One other remark goes kind of in the same direction. So you can write down here in the space of all matrices the subset of matrices which have rank k, and we have already seen that such things are is an open condition, so it's an open subset of this space of all matrices. So this has the structure of variety. And there's a map from here to the Grassmannian which sends A to the column span of A. And you can check, because I mean, this sits inside this big projective space, you can check like this, that G is actually a morphism. And of course, this column span is invariant, as we have seen under right multiplication by a certain general linear group. And I just wanted to point out as a kind of outlook, if you want to study algebraic geometry further, you could show that I mean, this surjective map, and in fact the Grassmannian in a suitable sense is the quotient of this variety U by this group action. So we haven't defined really what is an algebraic group, what is a group action, and what would it mean to be a quotient. But just as an outlook, like these things can be defined, and then you can make sense of this and see that this is such a group quotient of this very simple space U. And this can sometimes be useful. And the last thing that we want to do is there's a very nice symmetry property about the Grassmannians. And with the affine patches that we have now, the symmetry property can be shown very easily. So if you fix some k between 0 and n, and you look at this Grassmannian here, then the claim is this Grassmannian is actually isomorphic to a different Grassmannian. The ambient space is still k to the n, but we have gone to the complementary dimension. We went from dimension k to dimension n minus k, which means codimension k. And the proof, well, we can just write down the isomorphism that we like, because we start with a k-dimensional space and we send it to its orthogonal complement. So L perp is the orthogonal complement of L with respect to the standard bilinear form. So in other words, is the set of vectors x such that x with this usual kind of scalar product like pairing pairs to 0 with any y in the space L. And then from linear algebra, you know that if you start with a k-dimensional space and you have a non-degenerate bilinear form, then the orthogonal complement is of dimension n minus k. So this indeed gives such an element of this Grassmannian here. And you also know that the inverse of this map is just given by taking the orthogonal complement again, because somehow orthogonal complement of the orthogonal complement is the space itself in this finite dimensional space. So what this shows is that we can write down the map in the other direction, giving inverse bijections. So somehow we already see that there's a nice natural bijection from here to there. The only thing that remains is to show that F is a morphism. Once you show this is the morphism, of course, the inverse map is given by the same recipe, basically. So this will also be a morphism, and then we have shown that this is indeed an isomorphism. And to prove that it's a morphism, we now use these affine coordinates, right? So L in this Grassmannian, let's say we are in the patch U0. So let's say L is in the column span of such a matrix here. Then we claim we can write down what L perp is explicitly. To do that, we just do one big matrix multiplication. We form a new matrix here, which has a new block decomposition given by minus C and some unit matrix here. So this E is the how we write the identity matrix, and then you can just do this. You can just do this product and see you get the zero matrix out. And from this, you can check with some linear algebra that indeed L perp is exactly the row space of this matrix here, because you can see, I mean, somehow C has rank yeah, no, I mean, somehow, well, you can just see that this has full rank E n minus k. So this row space will indeed be of dimension n minus k. And this thing shows that all of the entries in there are in the orthogonal complement. And so for dimension reason, the orthogonal complement is indeed the row space like this. And so, well, you have described explicitly what F does to the column space of this. But now you see, why is this a morphism? Well, this here sits inside this big projector space. So what we have to show is that the Plücker coordinates on f of L are regular functions on this affine patch of the Grassmannians, but the Plücker coordinates here, they're just the maximal minors of this row matrix. And these are, of course, polynomials in the entries of C. And so these coordinates being polynomials means that F is a morphism, and this finishes the proof. So you have this kind of nice symmetry property. And often, sometimes if you want to prove something about one Grassmannian, it can be nice to switch this dimension here to something which then has a nicer geometric interpretation. Okay, that is everything that we want to say about the Grassmannians.